Well, good morning, everybody, and thank you for the opportunity to speak with you today. Our experience paper, Rethinking RRC State Machine Optimization in Light of Recent Advancements, takes a look at recently available advancements to the UMTS HSPA state machine. So the first question, why study new UMTS technology advancements? As we all know, LTE and LTE Advanced are the future. Well, as shown on this slide, UMTS HSPA networks will continue to comprise the majority of wireless broadband connections for many years to come. UMTS HSPA is forecast to make up 3.9 billion subscriptions extending out into 2019. It's much too large of a base to be ignored. Smartphone applications must run over these networks, and they need to be optimized for maximum performance. Let's begin by taking a look at the UMTS RRC state machine model. The UMTS RRC state machine manages allocation of scarce radio resources among network users. The UMTS model consists of idle, fetch, idle, DCH, fetch, and then the optional PCH states. While on idle, the mobile device radio uses a long DRX cycle or discontinuous receive cycle of several seconds and is turned off the majority of time. Idle is the lowest power state with minimal radio resource requirements. When users access the network, there is a large promotion delay penalty, typically of 1 to 2 seconds. This is for the idle to DCH promotion. Significant signaling is necessary between the mobile device and the network to configure the radio resources required for the DCH state. The promotion delays degrade application performance and user experience. While in the DCH state, the mobile device is transmitting continuously on dedicated control and data channels, and the mobile receives continuously on the high-speed downlink shared channel. This state has high radio resource requirements and high power requirements. A fetch is an intermediate state which uses low bandwidth shared and control data channels. The fetch channel was not designed with today's smartphone applications in mind and offers minimal benefits for most applications. It has been reported by others that some networks bypass the fetch state completely. So the delays on state transitions have significant impacts on mobile application performance. State machine optimization involves trading off application performance, mobile device battery life, and network radio resource capacity. Traditional optimization involves tuning state transition timers. However, general optimization is not possible, as optimizing performance for one application class comes at the cost of others. Application interventions, such as heartbeat packets, fast dormancy, or batching periodic transfers, have been investigated. Heartbeat packets can be timed by applications to maintain a desired state, eliminating unwanted state transmissions. Fast dormancy uses application-triggered signaling to immediately terminate the radio resource connection. Care must be taken when using fast dormancy because it's not properly supported in all networks, and it can cause mobile devices to bypass the fetch and PCH states and circumvent their benefits. Batching periodic transfers is used to reduce the number of state transitions that occurs when multiple applications with periodic transfers run asynchronously on a smartphone. However, due to the inherent design limitations of the UMTS state machine model, none of these methods is entirely satisfactory. The 3GPP recognized the limitations of the UMTS state machine design and developed multiple enhancements. In 3GPP Release 7, Continuous Packet Connectivity, or CPC, introduces a short duty cycle discontinuous transmit and discontinuous receive mode, which is similar to the microsleep used in LTE. The short duty cycle improves mobile battery consumption when no user data is being transmitted or received in the DCH state. Also, by eliminating null uplink transmissions, uplink interference is reduced and network capacity is increased. HSFATCH introduces a shared or common HSPA data channel, greatly increasing FATCH channel bandwidth more than 30 times, while also increasing user capacity. In Release 8, EUL-FATCH is introduced, as HSFATCH only provides a high-speed downlink channel, while still relying on the R99 RATCH channel for uplink. EUL-FATCH replaces the RATCH channel with a high-speed uplink channel. Further, enhanced FATCH also includes a longer discontinuous receive cycle in the FATCH state to reduce power consumption further. So, in order to study the impact of these new state machine enhancements, we need to determine if these features were widely supported by phones currently in use. These were optional features in 3GPP, and only a subset of available devices will support them. To do this, we analyzed the RRC connection setup complete message. This signaling message includes information fields that identify if a phone supports any of these features. The message is transmitted anytime a mobile sets up a connection with a network. We collected RNC data for more than 4 months and tabulated results, finding that CPC was supported in over 12% of the RRC connections, and HSFATCH was supported on just over 4% for the network that we studied. However, the Release 8 features were not well supported. We found it quite difficult to identify which phone models supported these features, as different build variants of the same phone model may or may not support a given feature. As an example, we found some versions of the Samsung Galaxy S4 supported the Release 8 features, while others did not. Once we determined support for the enhanced RRC features, we needed new tools to study their effect. A traditional method for identifying RRC state transitions is to measure the mobile energy consumption while in operation. Each RRC state has its own power consumption signature. However, these measurements can be quite noisy, requiring significant averaging to interpret the results. Another popular method is to infer state transitions by analyzing interpacket timing from a trace collected on the phone. ARO is an application available from AT&T, used by application developers for this purpose. Finally, there are wireless debugging tools that interface with the onboard chipsets, such as Qualcomm's QXDM, RIL Analyzer, or TEMS Investigation. These tools will provide a ground truth state for analysis. Some of the limitations of using these tools is that they require special devices with specific drivers and software loads to function properly. They're not generally available. We found the traditional measurement methods could not identify the use of CPC, of the CPC enhanced DCH state, with its discontinuous transmit and discontinuous receive. So in order to study this, we used over-the-air measurements to identify the RRC state transitions. The over-the-air measurements use an RF spectrum analyzer configured in zero span mode, which will measure the amplitude of the transmitted RF signal and gives us a picture of the RF envelope. Over-the-air measurements identify the DTX mode with millisecond accuracy. The DTX duty cycle and energy savings are then clearly measured. Additionally, we collected statistical data from the RNCs used in the target network. The statistical counters measure state transitions network-wide and allow a large-scale study of performance. However, this does require access to the network nodes to conduct such a study. So in this graph, we have the energy consumption measurement for a device transitioning through the various RRC states. If you look at the blue trace on the upper left of the graph, there's a 512 byte ping being sent. The ping is preceded by a 1 second state promotion delay. And it is then followed by a 2 second DCH tail time. The RF envelope here is shown in red and clearly identifies the beginning of the mobile device's transmission before it actually sends the data. After the 2 second DCH tail, the mobile drops down to the fetch state. And finally, it remains in the fetch state for 10 seconds. And then the red line here, that red line over on the right of the graph, that indicates another signaling burst as the phone returns to idle. For the device under test, average power consumption is 418 milliwatts while in the DCH mode, and power drops to 250 milliwatts while in fetch. And then finally, during idle, power consumption from the device is less than 30 milliwatts. So in the next graph, we see the energy consumption measurement for the same device with the CPC, discontinuous transmission, and discontinuous receive enabled. With CPC DTX, the transmit cycle is clearly visible and is shown by 40 millisecond pulses. It is also clearly visible that the DTX cycle begins immediately after the user data is transmitted. The state promotion delay, user data transmission, and DCH tail are all unambiguously identified by the RF envelope measurements. And from these measurements, we see that DCH power consumption drops to 314 milliwatts, or a 25% reduction. So to optimize a network using CPC, the method is to extend the DCH tail time. By extending DCH tail time, state demotions and subsequent promotions are eliminated between application packet bursts. The reduction is dependent on the inter-packet timing for a given application. To study this at a network-wide level, we relied on the use of statistical event counters present in the radio network controllers, or RNC nodes. These counters were downloaded to a database for analysis. So here we see reductions in the order of 40% when the DCH tail time is extended from 2 seconds to 4 seconds. And a further reduction occurs at 6 seconds. State promotions are also reduced by 39% for both RNCs. So the increased time spent in the resource-intensive DCH state will require additional network resources. However, somewhat surprisingly, the increases were quite modest. The graph on the upper left shows that DCH connections, simultaneous DCH connections, increased in the order of 10 to 13% when the tail times were doubled, and an additional 12% when tail times were extended to 6 seconds. We also observed that the use of the fetch state decreases when DCH tail time is extended. The increased DCH connections also caused little increase in downlink power within the test area. This is shown with the cumulative distribution function on the lower left. So for HSPA networks, when the base station transmission power is exhausted, no additional connections can be supported, and connections are blocked. Any increase in transmission power decreases network capacity. This is an encouraging result. Next, we examined the performance of the new HS-FATCH channel. To measure this, we conducted round-trip time measurements and measured for improvements in round-trip time and FATCH to DCH promotions. The improvement in round-trip time was significant, but far less than expected given the large increase in FATCH channel bandwidth. We found the limiting factor in performance was the use of the legacy R99 RATCH channel. This uplink channel uses a blind power control algorithm on the uplink with a slow power ramping procedure. This procedure is repeated for each transmission. So to further assess the channel, we used RNC counters that provided a measure of the average session throughput for the HS-FATCH channel. These counters indicated that in the downlink, the HS-FATCH channel was outperforming the 64 kilobit per second DCH state channel, highlighting its potential when coupled with an adequate uplink channel. So another part of our study was investigating the performance of the RRC state machine with popular applications. We used packet traces and the AR analysis tool to assess the performance of HS-FATCH and CPC for social media, streaming video, and VoIP applications. Our findings were that CPC is very effective for streaming and social media applications, reducing power consumption greater than 20%. For the voice over IP application under study, packets were sent every 20 milliseconds. And this rate is far too fast for the discontinuous receive and discontinuous transmit cycle used in CPC. As a result, the mobile device remained in the fully powered DCH state continuously. This occurred even during periods of silence. This suggests application tuning would be necessary for any improvement in battery consumption. And then the uplink channel in the FATCH state has very limited capacity. Data bursts greater than a few kilobits per second on the uplink trigger state promotions to DCH. So careful application tuning is necessary to use this state as it's currently implemented. So coming to our conclusions, CPC is very effective in increasing battery life and improving latency by allowing more extensive use of the DCH state. We found that the new HS-FATCH channel has greatly improved bandwidth, but only on the downlink. This limits the performance gains of HS-FATCH as it still uses the R99 channel for uplink, and really calls for the full implementation of the release feature set, which completes the FATCH state enhancements.